Hey folks, this is our big lesson of the unit on conservation of mechanical energy. The idea of conservation is one that is very important to science, and so we interact with a few conservation laws in this course. And so what I wanted to start with is what does conservation mean, or what does it mean to say that a quantity is conserved? So what does that even mean? And so there's a couple ways that we can talk about something being conserved in science. We can say that the total value of something that is conserved is constant. And so, in my silly classroom example of my motivation to eat chocolate, I pay money for chocolate and I get chocolate that has the same value in theory as the money that I pay for it. And so, value can mean monetary value, but in physics, it just means the number of joules is constant if we're talking about energy or something else. So the total value is constant. The total change in value is 0. And so that kind of leaves rooms for saying that, there can be an increase in this thing and a decrease, but there always has to be simultaneous increase and decrease so that the total change is 0. The kind of final thing to say something's conserved is that the thing can change forms or locations within a system. And so to say something is conserved is basically saying it can't really leave, that however much of that thing you have, you're stuck with that thing. The total value of that thing is constant. And so we're going to talk about energy. And so, there's the generic idea behind the law of conservation of energy. Law of conservation of energy. And so, that one is kind of very generic. And that one's just saying the total energy in the universe is constant. And so that's the umbrella that we're existing under, is that if we were to add up all of the energy present in the universe at every moment of the universe's existence, we would get the same number. Now, that's not how we're going to use conservation of energy. We're going to use it in a much smaller sense. And so we are going to talk about the conservation of mechanical energy. And so, mechanical energy leaves out bits of the story. In other words, we're going to talk about situations in which the type of energy involved is something that we don't study, and so we are going to pretend that it goes somewhere else outside of our purview. And so the way that we're going to define this, and conservation of mechanical energy, that's all the kinetic plus all the potential, is that in a closed system, the mechanical energy is constant. So there's a couple ideas here. So if there's a closed system, there's got to be an open system. That should have the opposite property. If in a closed system the mechanical energy is constant, in an open system the mechanical energy is not constant. So that's one idea. And so we're going to talk about closed and open systems in a minute. The other thing is, it's conservation versus constant, and they're almost two different things. And energy is always conserved, meaning the total energy in the unit is always constant. This is a law that we haven't as a community of humans, we haven't seen this violated. We have seen countless times the law of conservation of energy upheld by natural events in the universe. This is never broken, but we don't use in high school physics, we don't use this conservation of energy law the way that that's written. We use it in this way. So energy is always conserved. In specific situations, the mechanical energy is constant. And so we are, our job as physicists here is to decide in what situations we have constant mechanical energy, and then decide when we don't have it, and work with both of those systems mathematically. So we have to talk about this idea of closed system. So to say that a system is closed is to say a couple things. So it means that the net external force on the system is zero. So there is an absence of net external force on the system. That might be difficult to see in some situations. And then, so the thing that we're going to kind of work on is closed also means that energy cannot enter or leave the system. And so I think, without writing it, we can say open systems are the opposite. So if you encounter a system that's open, it means the net external force in the system is not zero, and it means that energy can enter or leave the system. So our goal is to kind of discern whether we have an open system or a closed system. And for now, we're going to do that with just our understanding of the types of energy that we have. So we'll hold on to this idea for a minute, and then let's talk about mechanical energy. So this law of conservation of mechanical energy is really saying if you have a certain amount of mechanical energy in your system, and that system is closed, no matter what that system does, if it remains closed, it will end up with the same amount of mechanical energy. We know that mechanical energy is a combination of types of energy. So I'm going to write this equation in a strange way so that it's formatted nicely. We know that there's three types of energy that go into mechanical energy. One of those types is spring or elastic potential energy. One of those types is gravitational potential energy, and one of those types is kinetic. So you'll notice that I have initial kinetic energy, initial gravitational potential energy, initial elastic potential energy. On the other side, we have final kinetic energy, final gravitational potential energy, and final spring potential energy. Now, this equation is not saying that you will have all three types of energy at all times, but it is saying that mechanical energy is defined as the sum of these three types of energy. And if mechanical energy is going to be constant, then the sum of them before some event and the sum of them after some event have to be the same. So you want to think of the left-hand side is before an event, and on the right-hand side is after an event. Your job in physics related to the closed or openness of the system is to identify the event as either coming from external forces or not, or if the event causes energy to enter or leave. So the big question, does the event involve external net force and or movement of energy in or out of the system. And so I'm going to hopefully illustrate this idea to you with an event that's like pretty easy to analyze. And so now that event is going to be a couple pages down the line. There we go. The event is going to be a ball rolling up a hill. And so we're going to say here's the base of the hill, and then here is that hill, and then there's a plateau. Okay, so the ball is racing toward the bottom of a hill. And so I'm going to use that phrase in problems. So racing toward the bottom of a hill means that it's actually at the bottom of the hill racing toward the base of the hill. So maybe I should say base of the hill. And what's going to happen is that ball is going to roll up the hill, and it's actually going to make it to the top of the hill. So we're going to like play with this idea of systems. The ball, and we're going to do this not all the time because I think you're going to get some like intuitive understanding here. If I were to draw a free body diagram for the ball, the ball is a bad example, but we have the force of gravity, we have the normal force, and really that's it for the ball. When the ball is like up here, we have the normal force, and we have gravity, and then when it gets back up here, we have the same thing. But the normal force changes direction with the surface. Okay, so we are going to consider two different systems here. System A is going to be just the ball. And so, we have like a couple different ways to think of this, but intuitively speaking, the ball is going to be moving at a certain speed. We'll call that V naught. And then at the top of the hill, assuming the ball is going to make it to the top of the hill, it's going to be moving at some final speed. And so, in your description of this, the ball's going to roll up a hill, and it's still going to be moving at the top, but you're going to want to understand that the ball slows down as it goes up the hill. Well, you want to also understand why that happens. So if you think about like the ball just rolling along the flat portion, the net force in the ball is 0. So in this situation, the ball is just going to coast. According to our like simplified version of physics, nothing's going to happen. However, when you get here, there's like an angle to this hill. So it's kind of like an inclined plane. Well, now the force of gravity is not perpendicular to the direction of motion. It's at like an obtuse angle. The direction of motion and the direction of gravity. If the motion is this way and the force of gravity is this way, the ball is slowing down due to gravity. Now, according to this situation, gravity is external. So mechanical energy is not constant. Okay, so that was like maybe a big leap, right? The ball's moving along at some speed, and it slows down. It slows down because both of these forces are external to the system. The normal force doesn't impact the motion of the ball, but the force of gravity, once the ball gets to the hill, the force of gravity starts to affect the motion. Normal force is always perpendicular to the surface, so it's actually never going to have an effect on the motion of the ball. But the force of gravity is. As the ball goes up the hill, gravity is pulling it down the hill. And if that didn't make sense, we studied inclined planes, so there's like the mg sine theta part of this. So the net force is actually mg sine theta. That is an external force. We have just identified this system as an open one. And so mechanical energy is not going to be conserved. The way that plays out in the equations is if we assume that mechanical energy is conserved, and we think okay, well, the ball is down here, So what type of energy does it have? It doesn't have elastic potential energy because that's crazy, there's no spring. It doesn't have gravitational potential energy because it's at the lowest point that it's going to be. It definitely has kinetic energy. And okay, if we get over here, or sorry, I actually have to backtrack there. We can't talk about this right now. We have to talk about the fact that it takes two objects to store energy. So this is an open system. The final kinetic energy it has is going to be less than the initial kinetic energy that it started with. So there is a loss of energy according to this. So this is not a conservation of energy situation if my system is just the ball. And so I want you to understand that single objects cannot demonstrate conservation of energy. So in order for there to be conservation of energy, there has to be more than one object in your system. So in other words, single objects are always open systems. So what I want us to do now to end the video, and I realize the video is getting pretty long, is I want us to consider a second system. Ball and Earth. So this is very common. And so now, like, the cat's out of the bag. When you are choosing a system, you should choose, if you wanted to talk about conservation of energy, you should choose the objects that cause the potential energies to exist. In other words, when you want to demonstrate conservation of energy, you want to make sure you include the Earth as well as any spring-like structures in your problem. So the ball and the Earth. If I go back to this picture, Newton's third law dictates that because there's a force of gravity acting downward on the ball due to the Earth, there is an equal and opposite force of gravity acting up on the Earth due to the ball. So when you include the Earth in your system, the force of gravity becomes an internal force. Okay, so ball and Earth. Fg is now an internal force. Therefore, the net external force is 0. This particular situation, the ball and the Earth represent a closed system. And so here's why, and this is what I crossed out above because I realized too late that I couldn't do it. It was for this one. So let's look at this. Initial amount of mechanical energy should equal the final amount of kinetic energy. In this example that I started to cross out, the ball at the beginning of this situation is at the lowest point on the picture. And so the ball only has kinetic energy. The Earth doesn't really, we're going to consider the Earth to not have kinetic energy, even though it clearly does. We're working just on the Earth here. So the Earth's kind of like, it's in our system, but it's too big to consider its own motion. Now, there's an event, and the event is the ball is climbing the hill. Now, there is a change in the motion of the ball. So the speed decreases, but it doesn't go away. So there is some amount of final kinetic energy. It's actually less. It is less than what the ball started with because when it travels up the ramp, it's going to lose speed because it's fighting gravity. The new understanding is because it is fighting against gravity to get up to this hill, it is storing energy in gravity. So the ball started down here, it is now at a greater height, and so the ball has obtained, or the system here has obtained, gravitational potential energy. And so this equation demonstrates conservation of mechanical energy. The value of mechanical energy is going to be constant. The system traded kinetic energy for gravitational potential energy. And so systems can store energy and systems can release energy depending on what they do. To say that kind of another way, the motion of the ball slowed down at the expense of changing the shape of the system. The Earth and the ball were this close together, and now they are this close together. And so in a future video, we will work with a mathematical example of this, but this video is plenty long.